begin recording. So you can have it. Now, other kinds of, so we've talked about linear motion, circular motion, about two other kinds of motion. Then we look at linear motion. Apart from linear and circular motion, what other types of motion can we talk about? Yes. Yes, Jaden. Asian, are you there? Jaden, go ahead.
Random motion.
Yes, sir.
Okay. Come again.
Random motion.
Random
Random
motion. Random motion. What is random motion? Jaden, you raised it, so explain. Share your opinion. What
the
is
movement
random?
of an object without a specific direction.
The movement or the technical word we use to describe is this is the non-directional or the haphazard, okay, the adjectives to describe this haphazard or non-directional movement of an object. Yes, so here the object has no specific direction. It has no specific direction. Okay, it can move to whichever direction, okay, given. An example of random motion. Yes, give me about one or two examples of random motion. Yes. Yes. Who is giving us an example? Elizabeth.
Please, Brownian motion.
Brownian motion. Okay. Brownian motion. Yes. More examples. So Brownian motion exhibits random motion. Random motion. Yes, John.
Sir, the motion of a drunkard man staggering about.
Staggering about in the road. Okay. Yes. The motion of a drunkard. Yes. What again? Nana Kwame.
Sir, please, the movement of gas molecules.
The movement of gas molecules or smoke particles.
Yes,
Okay.
sir.
Yes. These particles follow the direction of the wind. Okay. Whichever direction given by the conventional air current, they also follow. All right. So, and the types of motion, honestly, we can talk about a lot. We can talk about projectile motion. We can talk about oscillatory motion. We can talk about simple harmonic motion. So let's, and these are areas we'll be looking at in physics. They are major topics we'll be considering. So let's begin with linear motion. Linear motion. A linear motion, we've talked about some aspects of it. So the motion of a body in a straight line, okay, is what linear motion is about. Linear motion. Now, as we started with, a body is said to be in motion when there is a change in position of the body. Okay, so the key features or attributes of linear motion or motion is that there must be a change in position of the body. So if an object beginning from a point A moves to a point B, because there is a change in the position A to a position B, we can confidently say that motion has taken place. Is that okay? Now, when motion occurs, there are situations where we'll only be interested in the magnitude of the movement. Okay? And the magnitude of the movement is that distance between the 2 points A and B. Class, what is the name given to the shortest distance between any two positions? The shortest distance. Or instead of distance, let me use interval. Interval between the two positions A and B. That's the what? That's the length. Okay. So that's the length, or it can be distance. The interval between the two positions A and B. But do not forget that we can talk about distance covered or this length, okay, when there is change in position. If the body is still at A, we cannot talk about distance covered. We cannot also talk about length. Is that okay? So when we are only looking at the magnitude, the amount of movement, then we are looking at distance. There are some other situations where we won't only be interested in the magnitude of the movement, but we can also be interested in the magnitude and then the direction of movement. Okay, example, a body moves from a point A to a point B. Okay, so let me indicate this as X. So the shortest interval between the point A and B, this is what we are calling as the distance X. There can also be an instance where we are interested in the direction. Okay, so here we are looking at the interval between A and B and direction as well. Maybe, yes, as we have indicated, the interval between is X meter. But the direction is from west or left to right, or west, east. Over here, what have we added? We have added direction, okay? Once there is a consideration for direction, this quantity changes to be, what name are we going to give to this quantity, which exhibits both magnitude and then direction? Kweku?
Vector.
Length. Length is not different from what we earlier considered. Somebody is also talking about vector. Yes, which is under the same concept, but let's be specific. Nana Safo.
It's a vector quantity.
Yes, this is a vector quantity, but what is the name given to distance covered and then with consideration, or yes, by considering its direction as well? There's a specific name.
Displacement.
Displacement. Okay, so what I'm trying to say is that in a first situation, because we were only interested in the magnitude of movement, we said this is just the distance covered from A to B. Distance covered. In the second situation, we are looking at the magnitude of movement as well as the direction of the movement. So the same quantity, but we are adding direction to it, which this time we change from distance to displacement. Class, are you okay?
Yes, yes.
So when we talk about distance, distance is the magnitude of the movement. Simple. Magnitude of movement. Now, when we are interested in the direction of the movement, distance changes to be displacement. So we define displacement as distance covered in a specified direction. What did I say? Class, what did I say?
Distance covered in a
specified
direction.
And that is what? That is what?
Displacement.
Displacement. So a typical application is this. Maybe direct me from from one point to the another, maybe from the station to your house. Oh, the distance from the station to my house can be 500 meters. Okay. So here you are giving me an idea of the total length or distance to cover when I'm supposed to move from the station to your house. Now, if I want you to direct me to your house, you cannot just say, oh, from my house, just go through a distance of 500 meters. That alone cannot help me. So here you must add, oh, from the station, go through a distance of 500 meters from north, okay, to south, or north to west, east to whatever. You are adding direction. And so here, you are not just giving me a distance, but you are giving me distance and direction, which will take me to the location. Is that okay? All right. Now, when a body is in motion or is moving, the change in position occurs within a given time. So look at a body moves from a point A to B. The body moving from A to B would take place within a certain time interval T. Maybe when I'm starting, T is 0. After about 3 seconds, 4 seconds, I come to the location B. Okay, so what is happening? I'm covering different distances within, okay, a certain time interval. Okay, so when we look at how distance covered is changing or displacement is changing within a given time, it also gives us a different quantity. So we've talked about distance. We've talked about displacement. When distance changes within a given time, this quantity, distance changing with respect to time, gives us a different quantity. And what we call this quantity? When distance changes with respect, this is equal to what?
Speed.
This is equal to speed, yes. Speed. Okay, and so mathematically, speed is determined as distance
Distance over time.
over time taken. Now, in the same way, when distance covered in a specified direction also changes with respect to time, it also ushers us into a new quantity which we'll call as displacement changing with respect to time also amounts to the rate of change of displacement with respect to time gives us what?
Velocity.
Acceleration.
Velocity.
Okay,
Velocity.
I'm so happy with the divergent views. So the rate of change of displacement with respect to time is what we call as velocity. Velocity. So velocity is equal to change in displacement with respect to time.
Time.
So when displacement changes, please, you see, you cannot just say displacement, velocity is displacement over time. You must talk about change. Okay, there must be a change to produce velocity. There must be a change in distance covered to produce speed. If there's no change and we are talking about the same speed, the same displacement, you can't talk about speed and velocity. Please, are we okay?
Yes,
Right?
Yes, yes.
What I'm saying is that you cannot talk about speed. Speed cannot be just distance over time. When we are talking about speed, we are talking about change in distance covered. Change in distance covered over time. When we are talking about velocity, we are talking about change in displacement. There must be a change in displacement over time. Now, we'll talk about average speed and we'll talk about average speed and average velocity. And so you will understand what we mean by them. Anyway, let's talk about the average quantities before we look at acceleration. Then we can also talk about average quantities, such as average speed. With average speed, here we are talking about total distance covered, divided by total time taken. Example, Nana Kwame moves from a point A So you started your journey from a point A, then move to a point B. The distance covered is X. The time taken to move from A to B is T1. Nana Kwame also moved from B to C. Then cover the distance X2. Okay. Then the total time taken to move from B to C is T2. If I must calculate the average speed, then the total distance covered over total time can be equal to x1 plus x2. This is the total distance covered from moving from A to C. Then the total time taken can be T1 plus T2. This would give us the average speed. If I'm to calculate Nana Kwame's speed, okay, the speed from A to B can be different from B to C. So I can determine the speed, Nana Kwame's speed, okay, from A to B. Okay, now, the distance, when Nana Kwame started, he had not covered any distance, 0. So if I'm looking for the speed from A to B, this will be equal to change in distance covered. Initially 0. Then after T1, he covered a distance x1. So the change in the distance covered will be x1 minus 0, which is the same as s1 over the time interval T1. If I'm to determine the speed of Nana Kwame in moving from B to C, then it can be B to C can be x2 over T2. However, if Nana Kwame's speed was uniform, then I can subtract. If Nana Kwame had been moving with a uniform speed, then his speed can be the total distance x1 plus x2 over the time interval, which is this plus this one. And this is if he was moving at a uniform speed. Class, are we okay?
Yes, please.
As to how to determine the average speed and then the speed. Okay, we'll be solving questions okay, we are just going through the theory. We'll be solving questions, and so you understand how to go about this. So that is it with average speed. Okay, average speed and then average velocity. For average velocity, we can also talk about the total displacement over the total time. Now let's talk about another quantity. acceleration. Acceleration. Class, what is acceleration? Let me use, what is acceleration? Can somebody share with us what we mean by acceleration? Yes, can somebody share something with us? What is acceleration? All right, okay. Della, go ahead. What is acceleration?
It is the change of the velocity of an object in respect to time.
Thank you. So we define acceleration as the rate of change of velocity with respect to time. Okay. The rate of change of velocity with respect to time. So mathematically, we say that acceleration A, this is my short form of acceleration, is equal to delta V on T. It means that for acceleration to take place, there must be a change in velocity. Just as to talk about velocity, there must be a change in displacement. Over here, there must also be a change in the velocity to talk about acceleration. So you cannot simply say that acceleration is V over T. This must go with change. So I expect to see that this symbol delta. This is what implies or talks about the change, delta V. Practically, what is acceleration? Now, whenever a body is stationary, it's just at one place, the body's velocity is 0 or the speed is 0. If you start to walk, is your velocity still 0?
No, please.
No. Now, so when you begin moving or walking, your velocity is increasing a little bit. Now, if you begin to run, your speed or velocity is increasing, right? Good. So it means there's a change in your initial velocity and then your final velocity. And because there is a change in these two velocities, we say that you are accelerating. Another instance, when you are in your father's or mother's car. Okay. Henry, this is what I mean. If you are just standing at one place, your velocity is 0 because you are stationary. Because you are stationary or at rest. Now, if you begin to walk, Henry, is your velocity still 0? Henry, I'm asking you a question. Is your velocity still 0? No. Now, if you begin to run, your velocity or your speed will be increasing. Now, because there's a change in your old velocity and your new velocity, let's assume V1 is the velocity when running. So, because if I find the difference between your final velocity and your initial velocity, I can get something, a change. So delta V will be equal to V1 minus V naught. V naught. V naught is actually 0. Okay. So this is giving us a change. And because this is giving us a change, we can say that A, we define acceleration as change in velocity, delta V over time. And so we have V1 minus V naught. And because there is a change, I can say that you are accelerating. Class, are you okay? Class, are we fine?
Yes, please.
If you have any question, ask. Another application of acceleration is this. When you are in your mother's car or father's car and they want to speed, they step on the accelerator. Okay. What they are doing is that because maybe as before stepping on the accelerator, the speed wasn't so much for them. Okay. They now step on the accelerator to cover more distance within a short time. And so the speed before and then the speed now, when you subtract, you have a change. So delta V will be equal to the speed, the final speed minus the initial speed. And this change must occur within a given time, t. And so when you divide the change in velocity by the time, you can have acceleration A. So we define acceleration as change in velocity with respect to time. Acceleration can be positive. Acceleration can be negative. Acceleration can be the same or be 0. Okay. Now, when acceleration is positive, all that we mean is that the body's speed or velocity is increasing with time. Okay. If acceleration is positive, practically what we mean is that the body is moving with increasing velocity with time. So maybe initially my velocity is 2, 4, 6, 8, 10. What is happening? My velocity is increasing with time. When the velocity increases with time, you have acceleration being equal to a positive value. That is when we say that the body is accelerating. Are we okay? So acceleration, positive acceleration goes with increasing velocity. Class, what did I say? What did I say?
Positive acceleration goes with increasing
velocity. Okay, so positive acceleration goes with increasing velocity or speed. Okay, now negative acceleration, which we call as deceleration. Let me write some keynotes for you. So I said acceleration.
Mr. Edria, please, we can't see your board. We can't see your board. It's gone. I can't see it here.
Is that how does it look?
It's just a blank black screen.
Oh, then I think it's a network problem from your end. Can you rejoin?
Okay.
I'm also recording, so you try and reconnect and let's see if that will fix the problem.
Okay.
So I said acceleration is the rate of change of velocity with respect to time. The rate of change of velocity with respect to time. And so mathematically, acceleration is equal to delta V. The delta V will mean final velocity minus initial velocity over time. Okay, so A is equal to V minus U over T. Then I said acceleration can be positive. Acceleration A can be positive, negative, or zero. When acceleration is positive, when acceleration is positive, the body moves with increasing velocity or speed. So when acceleration is positive, it means that the body's velocity or speed is increasing. And example, maybe starting with a velocity of 2 meters per second squared, then moving to 3, 4, 5. So the body's movement occurs within increasing speed. Then the body is said to be accelerating. Now, when acceleration is negative, it's negative. Yes, I want somebody to brainstorm and tell me something. When the acceleration of a body is negative, what does it mean?
The velocity decreases with time, also known as deceleration.
Good. So here the velocity is decreasing, or the speed is decreasing with time. And this is what we call as a deceleration or retardation. Yes. Okay. So when acceleration is negative, the body's velocity or speed decreases with time. So a negative acceleration is what we call as a negative acceleration is known as deceleration or thank you, deceleration or retardation. Now, class, when a body's acceleration is 0, what does it mean? When a body's acceleration is 0.
The body is not in motion.
Sorry to disappoint you. When the body's acceleration is 0, what does it mean?
Stationary.
The body is what?
It has a constant velocity.
Okay. All right. I think somebody has said it. Please, when the body's acceleration is 0, it does not mean the body is stationary. No. It means that the body, velocity. Yes, it has a constant velocity or constant speed. The body has a constant velocity or constant speed. Application. You see, during interschools, some athletes are so good to the extent that you just be standing, okay, within the spectators and then be cheering. Hey! Why? Because you feel the person can run. If the person can run, what does that imply? It means that maybe when the person started, okay, the athlete started with a certain speed and has managed to finish the race with the same speed. So when he started, look at the strides, how he was moving, he or she was moving the legs. He was able to maintain the same speed and finish with it. And so you'll be so ecstatic, as if you are the one running. No. Okay. Yes, such movement is what we call as constant speed motion or constant velocity. You realize that the speed or the velocity of the person doesn't change with time. But does that mean the person is stationary? Does that mean the person is stationary? No. The athlete is in motion, but it is just that his velocity or speed is the same from start to finish. Is that okay? Now look at when an athlete or a body moves in that manner, why do we say that the acceleration is 0? Acceleration A is equal to delta V over T. Assuming the athlete's starting speed is 5 meters per second. 5 meters per second squared, and is able to maintain the same speed till the ending of the race. So he finished with final velocity of also 5 within a time interval T. When you subtract, the numerator is 0. And once the numerator is 0, it means acceleration A is 0. So when the speed of a body does not change, the acceleration of the body is equal to 0. Okay. So, but do not think that when a body is stationary, his acceleration is 0. When the body is stationary, it has no velocity. Okay, only not to talk about the change. And so we can't talk about acceleration here because the person has no speed in the first place. Class, are we okay? Are we okay?
Yes, sir.
All right. So let's put everything together. You see, in our discussion, we've talked about distance. We've talked about displacement. We've talked about speed. We've talked about velocity. And finally, we've talked about acceleration. There is something which features in all these examples we've talked or we've mentioned. I think we also talked about time. If you look at distance, we are looking at the interval between 2 points. It's just the distance. This quantity has something to do with amount, or it is a quantity-based something. It has nothing to do with direction. Displacement, we are talking about distance covered, however, in a specified direction. Speed. So we are looking at the distance covered, okay, over time, the time taken. Velocity, the distance changing displacement over time. And so we can put these quantities into two main umbrella, which we refer to as scalar quantities and vector quantities. And I'm sure you did this under measurement. And the measurement, I'm sure you talked about scalar quantities and vector quantities. What is a scalar quantity? Class, what is scalar quantity? Nana Kwame.
Say please, a scalar quantity is a quantity that has only magnitude but no direction.
Thank you. So a scalar quantity has only magnitude and no direction. So let's put whatever we have here under scalar and vector. By the way, what is a vector quantity? Eva, what is a vector quantity? Eva, go ahead. Oh, ACN. Let me go to ACN. Abeka.
Vector quantity. It is a quantity which has both magnitude and direction.
Good. So vector quantity, we have both magnitude and then direction. Let's put whatever we've discussed so far: distance, displacement, speed, velocity, acceleration, and time under these two umbrellas. Okay, so I'm going to call you, get ready. I'm just going to call you, and then you put one of these under the classification for me. So I'm going to the platform and pick your names from there. Okay, so Belinda, are you there? Belinda. Hey. Belinda. Okay. Let me throw it to you. Distance. Where will you put distance? Anna, scalar and vector.
Scalar.
Where will scalar go? So distance will be here. Displacement.
Vector.
So displacement is under vector. Speed.
Scalar.
Speed is scalar. Velocity.
Vector.
Velocity is vector. Acceleration.
Vector.
Time.
Scalar.
Time is scalar. Let me add a few. Where will you put age? Where will you put age?
What is age?
Age, A-G-E. Where will you put H?
Vector.
Why?
Scalar.
Why? Who said scalar? Who said vector? Where will you put H? Ato? Ato, what did you say in the first place?
Scalar.
Okay, why? Ato, why?
Age.
Ato, simple. Age is a time. You are 16 years. Don't forget 16 years is a time. Okay. So age will be an scalar. Now, where will you put currency? Hey, Asura, Teddy. Where will you put currency? Nana Kwame.
Scalar.
Scalar. Why? Because currency is money, amount. Okay.
Yes, sir.
Hey, temperature. Where will you put temperature? Nanajua. Even though I have no Nanajua, but somebody must answer. Kweku, where will you put temperature?
Scalar.
Scalar. I'm sure you'll be surprised if you are to visit the hospital and after your body temperature is has been taken, the nurse will sound like, oh, your body temperature is maybe 20 degrees Celsius west. Hey, you'll be shocked. What has west gotten to do with temperature? Your height is 1.2 meters north. Hey, nice. So okay, so these are the reason why. Okay, these quantities are placed under scalar because they are just quantitative amounts. Please, any question? Any question? In terms of units, you see, you have done measurements. What is the SI unit of distance? What is the SI unit of distance? Meter. Meter. Usually with units, we don't pluralize it. Meter. Displacement. The same distance, but in a specified direction. So, speed. What about speed? Don't forget, speed is what? Distance covered or distance over time. So, meter per
second.
Good. Meter per second. Velocity, the same thing. Meter per second. Acceleration.
Meter per second squared.
Because yes, because acceleration is delta V over T. Delta V is in meter per second, then time second. So we have meter per second squared. So you must identify their units as well. In dimensional analysis, it means that distance and displacement have the same dimension, capital L. Then speed and velocity also have the same dimension. So what's the dimension of speed and velocity? What's the dimension of speed and velocity? Hey, dimension.
LT minus
LT minus 1.
LT.
LT minus
LT to the power minus 1. Yes. So LT to the power minus 1. So do not forget these basics. All right. Now let's move on to graph of motion. Please, if you have any question, do not hesitate to ask. Before we look at graphs of motion. Graphs of motion. A body moving and as a result covering some distance occurring within a given time. The body covering a certain distance in a specified direction within a given time can be plotted on a graph. In plotting of graphs, we always place the independent variable, okay, as the x or on the x-axis. Then the dependent variable is always plotted along the y or the vertical axis. So if you have any graph, whether graph of motions or whatever, then I'll give you the notes. So graphs of motion. So in plotting a graph, we always put the dependent variable. The dependent variable is always plotted on the vertical axis. Then the independent variable is plotted on the horizontal. So in a straight line graph or straight line graph, yes, so in a straight line graph, this is
Henry.
These are three different straight line graphs we can have. Come in. Henry, mute yourself, okay? So in a straight line graph, please, what is the equation of a straight line? What's the equation of a straight line? I'm testing your math. What is the equation of a straight line? Oh, anybody? Equation of a Eresi, Nana Kwame.
Y is equal to mx plus.
Okay, y is equal to mx plus c. Nana Kwame, where y is equal to what? Of course, the vertical axis. M is the what?
Gradient.
The gradient or the slope. And then C is the
y-intercept.
Y-intercept. Thank you. Then X.
Coefficient.
The horizontal. Now I have, these are straight line graphs. 1, 2, 3, yes. What do you think will be the equation for the first graph? What will be the equation for the first graph? Yeah, I'm testing your mathematical strength. What will be the equation for the first graph? The platform is quiet. Hey. What will be the equation for the first graph? Anybody to try? Just give it a try. Adam, try. Adam, try. Once your microphone is on, then you are a suspect to contribute. Adam, your microphone is still on. No? Eva. Laura. Charlie. Hey, Omwada. Okay, Nana Kwame. Nana Kwame, what do you think will be the equation for the first graph?
Sir.
Mm-hmm.
Why?
Mm-hmm.
Repeat the question again.
We are writing, this is a linear graph. 1, 2, 3 are linear graphs. We want to write equation for 1. What do you think will be the equation for 1?
Y is equal to mx plus 1.
Where is the Nana Kwame? Where is the 1? Okay, I saw. Where is the 1? This one.
Yes, please. Yes, sir.
Is it this one?
Yes, sir.
Yes, Nana Kwame, I'm listening.
Yes, sir, please, that one.
Nana Kwame. How can this be? Okay, please, do I have any other contributor? Before I come in. Okay, so this is the equation for 1. Okay. Y is the vertical axis. X is the horizontal axis. M will be the gradient. And then C would be where the graph cuts the vertical axis. C. So this point is the intercept on the vertical axis. So this will be the equation. Now, what do you think will be the equation for the second graph? The second graph. Anybody to try the second graph? Hey. Okay. Over here, the only difference is that, okay, looking at the second graph, what do you think is the intercept on the vertical axis? Where does the graph cut the vertical axis? Class, where does the graph cut the vertical axis? Hey, Eresi.
At 0.
0, yes. So the equation will be y is equal to mx, just mx. Because C is 0. because C is equal to 0, the graph cuts this at the origin. And so this is the equation. 2. What do you think will be the equation for the third line? Whoever wins this or gets this right wins a traveling visa to Dubai after COVID. What do you think will be the equation for the third graph? Just say it and win a visa to Dubai after COVID.
Y is equal to C.
Charlie, you win. You win. Explain to us why. Why do you think it will be Y is equal to C?
Because there is no slope or gradient. The slope or gradient is 0.
M is 0.
Means
M
the
is
slope
0.
or gradient, yes.
Yes. And this is where it cuts the vertical axis. So it has an intercept on the vertical axis. Is that okay? And then a last one. I want to see. Then we go to physics. Please, here I'm doing math. I want to see how you can apply all that we've said to this. What will be the equation of this line? It will be under. What will be the equation of this line? You know, physics and maths actually move together. So let me disturb you a little bit with this simple mathematical aid. What will be the equation for this line? Ayo, come again. Ayo. Nana Kwame. Are we here? Hello, class. Are you here?
Yes, sir.
Yes, sir, we are here.
What's the equation of this line? Okay. This will be Y is equal to, does the line cut the vertical axis?
Yes.
So there will be a slope. There will be intercepts. But you see, if the graph is like this, then the gradient will be a positive gradient. Okay. If I well noted, if the graph is like this, the slope will be a positive. If the graph is like this, the slope is a negative. Because anyway, we'll come when we get to it, you understand. So we've started graphs of motion, you understand. So here the gradient M is a negative. So minus mx plus, yes, there is an intercept and it cuts the graph at positive value. 0 up positive, 0 down negative. And so C is positive. So plus C. So when you have something like this, gradient is negative, and so this will be the equation. All right, we'll be applying it. So if I'll do that, I'll do that. So that's it. So for graphs of motion, usually the dependent variable is always plotted on the vertical axis. The independent variable is plotted on the horizontal axis. If you look at equation of straight line, y is equal to mx plus c. C is a constant. And we just saw that it is where the graph cuts the vertical axis. Okay. But a change in x would affect y. So it means that y depends on x. Meaning y is the dependent variable. It depends on x, and x is the independent variable. That is why whenever we are plotting this linear graphs, we place y on the vertical and then place x on the horizontal. So in plotting of graphs, the dependent variable is always on the vertical, and then the independent variable is always placed on the horizontal axis. Class, are we okay?
Yes, sir.
Yes.
All right. So in graphs of motion, we are always looking at how the distance covered with time. Okay, the displacement with time. What is the velocity with respect to time? So all these quantities depend on time. Time doesn't depend on them. Okay, if you are Usain Bolt, world's fastest person, we are looking at the distance you can cover within the everlasting time. So Usain Bolt during his time said was the fastest man on earth because he could cover 100 meters, a distance of 100 meters within 9.26 seconds. So we are looking at what you can do within the given time. And so T is always along the horizontal time. Then the rest, whether distance, whether displacement, velocity, which depends on time, is placed on the vertical axis. So that's the whole nitty-gritty of graphs of motion. Any question? Any question? No question. Now, on the graphs of motion, let's look at the different graphs of motions we can have. We can talk about distance time graph. And the distance time graph, we are plotting the distance covered by a body within a given time. Now for distance time graphs, what are the different kinds of graphs? We can have uniform speed graph or motion. We can talk about uniform speed. Motion or graph. Let me give you data to explain this. We have a table of distance against time. So this is distance S in meter against time in second. So at a time t is equal to 0, distance covered is 0. At a time t is equal to maybe 1 second, distance covered 2. At a time t is equal to 2, this is 4. 3, this is 6. 4, this is 8. If you have such a data and then you plot, you see, we have the body is covering equal distances within equal time interval. So when you plot such a motion, 1, 2, 3, and 4. You have 2, we have 4, we have 6 here, then finally we have 8. At t is equal to 0, the distance covered is 0, so we are starting right from the origin. At t is equal to 1, the distance covered is 2. At t is equal to 2, distance covered 4. T is equal to 3, distance covered 6. T is equal to 4, the distance covered is 8. When you join the plotted points, this is what you have. This is what you have. Now, when a body moves that it covers equal distances within equal time interval, this is, we describe such motion as uniform speed motion. Why uniform speed motion? Let's find the slope of this graph. And in determining the slope, we are always picking 2 points on the straight line. Okay, it can be this, or that. Any 2 points. So let's assume I am picking this and then this one, the first point and then the last point. So the slope will be changed in the vertical over change in the horizontal. So delta S over delta T. So delta S over delta T. Change in the vertical. The maximum distance is 8. So 8 minus the minimum distance is 0 over change in the horizontal. Maximum time 4. Minimum time 0. So I have 2. What do you think will be the unit? Distance in meter, time in second. What do you think will be the unit?
Meter per second.
So this is 2.0 meter per second. Now, Nana Kwame can also decide, no, I'm not interested in this point. I'll take different points. So Nana Kwame can also pick this one and then this one for his slope. When he decides to use this, then his slope would be equal to change in this, the vertical delta S over delta T. So his maximum value is 6 minus 2 over minimum value 3 minus 1. And this will be equal to, what will be the value of this slope? What will be the value?
2.
This
2.0 meter per second.
This is also 2.0 meter per second. Okay. Then Ewuresi can also say, I want to go for this point, this one and this point. So she want to pick the slope using this. Okay. So if this, the maximum is 6. Maximum is 6. The minimum is 4 over maximum time 3 minus minimum time 2. So Ewuresi is getting 2 over 1, which is also 2. So we realize that no matter the points taken along the straight line, what you are getting for the slope, what we are getting for the slope is uniform or the same. Okay? And so we see that because this has a uniform slope, which is equal to velocity, then such motion is termed as uniform speed. Okay? Please, here we look at distances. The vertical, we look at distances. And so distance over time. And so we realize that the slope, which is equal to the speed, is the same along the straight line. And so this is termed as uniform speed motion. So for a uniform speed motion, the body covers equal distances within equal time interval. That is the definition of uniform speed motion. The body covers equal distances within equal time interval. Please, is that okay? Please, are we okay?
Yes,
Yes,
sir.
please.
And if you have a distance time graph or displacement time graph, the slope, take note, the slope of a distance time graph or distance or displacement. I'm using the two at the same time. The slope of a distance or displacement against time graph is equal to the speed or velocity of the body. So if you have a distance or displacement time graph, the slope is equal to the speed of the body or the velocity of the body. So whenever you are given the displacement time graph or a distance time graph, and you are asked to find the slope, and you are asked to find the speed or the velocity, the slope is always equal to that. Take note. Please, any question? Any question? All right. Then we can also have another situation. The other situation is this. The same data, but this time, this is how I'm changing the data. Time is the same because time independent variable. But at t is equal to 0, we have 8, 6, 4, 2, and 0. Class, what do you think is happening here? What is happening in this situation? What is happening? I'm just changing the values. Okay, at t is equal from 8 to 0. And here we see that the distance covered is decreasing within equal time interval. And when you plot such a graph, at t is equal to 0, distance covered is this. At t is equal to 1, distance covered is equal to 6. At t is equal to 2, distance covered 4. At t is equal to 3, distance covered 2. And then at t is equal to 4, So such a graph is like this. It's a negative graph. It's a negative graph. So when you plot, when you determine the slope, okay, change in distance over time, or the change in time. Change in distance, the final distance, which is 0, the final distance covered is 0. 0 minus the initial distance, which is 8, over the time interval. The final time is 4. The initial time is 0. And this is also equal to negative 2.0 meter per second. Okay. This is also an example of uniform speed motion, but the speed here is decreasing. The body's distance, okay, is reducing towards the starting point. So the speed is a decreasing speed. And this is uniform because this value is the same along the straight line. Class, are we okay?
Yes, sir.
Are we okay? So this is another example of uniform speed motion, but here it's a negative speed because the body speed distance covered is decreasing and coming back to its starting point. The reason for which we have a negative this value. Please, any question? And this is the same for whether it is distance time graph or displacement time graph. Take note. And so here too, the slope is equal to the velocity of the body. Then another possible graph. Let me quickly change the values and then use that to explain something to you. Time doesn't change. The time can be in equal intervals or non-equal intervals. But over here, we are looking at a changing something. And the changing something is this. The distance covered. At t is equal to 0. Distance covered is 0. At t is equal to 1, maybe 2, 3, 5. At t is equal to 3, we can have 9. At t is equal to 4, you can have 12. This time around, the distance is increasing, all right, but not in equal intervals. Okay? The distance is increasing, all right, but not in equal intervals. When you plot such a graph, as in distance against time, this is what you have as your graph. This is what you have. When you plot set information, this is what you have as your graph. Now, over here, we cannot have a uniform slope because the graph is not a straight line. Class, are you there? Are we there?
Yes, sir.
Yes, sir. Your responses is as if you are tired. We've just started. You cannot be tired. So just urge yourselves and let's finish. So over here, because it is not in a straight line, you cannot have a uniform slope for every. You can only determine the slope within a given time. you can only determine the slope within a given time t. This is 1, 2, 3, 4, 5. So I can only, maybe I want to determine the slope, okay, within a time t is equal to 3. So I draw a tangent to the curve through the time. And this is what I mean by the tangent. So there's the time I have considered. So I draw a tangent through the time. Okay. So I'm only interested in determining the slope at t is equal to 3. So what I do is that I trace t is equal to 3 to the distance maybe this is x1. And so I'm looking for the slope within this time. So this is it. Over this. So the change in the distance will be delta s is equal to x1. There's a maximum time within the given, so maximum distance x1 minus the minimum is 0, minus 0. Then, so the slope for this graph is equal to x1 minus 0 over the time. This goes with t3, which is 3 seconds minus 1 second, 1. This is how I can find the slope. I can also decide to, let me determine the slope at t is equal to 4. So at t is equal to 4, I draw a tangent through the time. Okay. I draw a tangent to the time and use this triangle to determine the slope. So for a non-uniform, this is said to be non-uniform because you can only find the slope within a given time. So here you can calculate the slope within a given time t. So the situation can, or the question can ask that, oh, find the slope at time t is equal to so and so. Okay, so you can only calculate the slope within a given time. And the slope of a distance time graph or a velocity time graph or a displacement time graph is equal to the speed or velocity. And so in a situation like this, the slope is known as instantaneous speed or velocity. The slope of such graph is known as instantaneous speed or velocity. The instantaneous simply means that the speed or velocity is within a specified or given time. Class, are we okay? Class,
Yes,
are we
sir.
fine?
Yes.
So,
Yes.
good. And this is known as non-uniform velocity motion. So this is a non-uniform velocity, non-uniform speed or velocity motion. It is non-uniform because different times would give you different speed or velocity. So it is not the same. Unlike in a straight line where the slope is the same throughout. Over here, it is non-uniform because we can only determine it for different times t. Please, if you have any question, ask. Quickly ask, and then if there is something to add, I add, and then we move. So my question to the house is that what is a uniform speed motion? What is a uniform speed motion?
A uniform speed
or uniform velocity motion?
A uniform speed
motion
motion
whereby your body covers equal distances with
whereby
equal
a
time
body.
interval.
Okay, you are both rhyming, but I heard everything. So the motion of a body where the body covers equal distances within equal time interval. Okay. Why is the velocity of such motion said to be uniform? Why is the velocity of such motion said to be uniform?
Because the distance covered is equal to the time taken.
Come again. I need more clarification. Why is the velocity of
because the distance covered is equal to the time taken, or the equal distance covered is equal to no.
Okay, Adam, let somebody else come in. Della, come in. Why is the velocity or the speed of such motion said to be uniform?
Because the distance against the time will be equal to the speed of the object or the body.
Okay, all right. Yeah, actually, come in. Yeah.
It is set uniform because the change in the distance and in the time is constant.
Okay. All right. Okay, this is what I also add. It is uniform because when you plot such motion graphically, the slope is the same along the straight line. So it actually bears its name, uniform speed motion, from the fact that the graph has the same slope along the straight line. Please, are we okay? So because the slope, which is equal to the velocity or the speed, is the same along the straight line, the reason for which such motion is described as uniform speed or velocity motion. All right. Okay, now for a non-uniform velocity motion, why do we call the slope as instantaneous? for a non-uniform, why do we call the slope as instantaneous velocity or speed? Why?
Please, because you can only calculate for the slope at a given time or at a given instant.
Thank you. More views. Nana Kwame, Dela and Co. Why do we call the slope as instantaneous? If you have something to add to what Erefua is giving us. Dela, Nana Kwame, Ayo and Co. Contribute. ACN, I'm still with you. Okay, Dela, go ahead.
The slope curves along the graph is not constant.
Yes, the slope is not constant or it's not uniform. The last, so add something.
So it curves along the graph, like when it's going.
Okay,
it's not straight.
It's not straight. So you can determine the uniform slope, which is the speed or velocity for the entire motion. You can only do it for a particular instant or time. Is that okay? Please. The reason for which this is known as instantaneous velocity. All right. I want you to use today. Our next meeting is on Friday. I want you to look at this carefully to tell me what deductions can we make from a non-uniform velocity motion. For a non-uniform velocity motion, what are some of the deductions or positives? What can we derive from a non-uniform velocity motion? We've seen that we can determine the velocity within a given time, but there is something else which I want you to look at, and so we'll discuss in our next meeting. Is that okay? So if you have any question, ask. If you don't have any question, then this is where I draw the curtains on our meeting today. We'll continue with the same concept on Friday. I believe we've had, though this is our maiden edition, but we've had a very nice interaction. Please, if you have some concerns, do not hesitate to forward to me on WhatsApp personally, so I address it for you. Is that okay?
Yes, sir.
All right. So, I mean, we'll end here and continue on Friday. Until then, please take care of yourselves and bye-bye.
Bye.
Bye. All right. So bye-bye to each one of you.
Bye.
So please the note too.
Bye.
Bye.